Hi friends. So in the last part of the video, we discussed about what monolith application is, what are their problems, why people move to microservices, and how microservices help people to move and become cloud native applications. When we talked about microservices, we talked about containers, and we understood like how container makes it easy to deploy microservices in the various environments, um, how it makes it easy from the deployment perspective. And then we hit upon one issue, right? That when we hit and when we scale up to, let's say, thousands of containers, how do we manage them? And we talked about the container orchestrators, and one of the container orchestrator is Kubernetes. So in the current video, we will talk about what Kubernetes is, what are its main features, and how it helps us. So today's agenda for this video is following. So we will discuss what Kubernetes is. We will discuss about the need for Kubernetes. We will discuss basic features of Kubernetes. We will discuss about the Kubernetes architectures. We will discuss the main components of Kubernetes. And finally, we will discuss one of the very central topic of Kubernetes, which is Kubernetes networking. So let's move to the next slide, and we will talk about what Kubernetes is. So as the slide says, Kubernetes is an open source system for automating deployment, scaling, and management of containerized application. Okay, the three terms: automating deployment. How do you deploy different containers? Okay, scaling. How do you scale? Let's say your microservices from one instance to 100 instances, or from 100 instances of microservices to, let's say, 10 or 15 instances based on demand. Okay, and then how do you manage them? By managing, we mean if you want to upgrade them, the version of the software, if you want to roll back the latest version to a previous version of the software, if you want to apply some sort of security policies around them. Okay, okay, if you want to implement rule-based or role-based access to these applications, how do you do that? So all of that is handled by the Kubernetes. Okay. So what Kubernetes is, from where it came. So Kubernetes was started by Google. Okay, and when Google released it with V1.0, okay, they donated it to the Linux Computing Foundation. Okay? And what Linux Computing Cloud Native Computing Foundation is, it is one of the sub forum of the Linux Foundation. Okay, and the idea is that this Linux Foundation and combined together with Cloud Native Computing Foundation, they are responsible for Kubernetes. Not only Kubernetes, they are also responsible for some of the sub-component of Kubernetes, that which we will just cover the next set of slides, and then we will go to a demo as well. But the high-level idea is Cloud Native Computing Foundation is the forum which is nowadays manages Kubernetes and Kubernetes subsystem. Okay. Now, just to give you an idea, I mean, how good Kubernetes is. So Kubernetes is derived from Google's Borg system, okay, which was the Google's secret, or at this point of time, a secret system which Google used to use to manage their thousands of, work jobs, which are scheduled across maybe thousands of servers or the host across different geographies. And it was successfully able to handle that. Okay, so with that in mind, let's dive deep how Kubernetes is able to achieve what it can and what exactly is the architecture of Kubernetes. Okay. Okay. So we talked about what Kubernetes is, and before we go dive deep into the architecture, let's briefly talk about what are the things or what are the primary responsibility or what are the primary features Kubernetes offers us. Yeah. So top of them is automatic bin packing, which means Kubernetes automatically schedules container based on resource needs and constraints. Okay, so for example, it can decide to spawn a certain Microsoft services 10 instances based on the demand it sees. Okay, and similarly, it can scale down to 2 microservices instance only for a particular service based on the demand. So it knows what are the resources available to it, how many max number of instances can schedule at given point of time, what is the minimum number of instances you can schedule at a given point of time, and depending on the resource availability and the demand and the max and min configuration, it can automate the deployment. Okay. Next is designed for extensibility. What does it mean? A Kubernetes cluster can be extended with the new custom feature without modifying the upstream source code. It's still complicated, right? So it simply means that, okay, you have deployed a Kubernetes cluster, which is, let's say, tied to a particular version of the software. It provides interfaces using which you can extend the features of your cluster. Okay, so that's all it talks about. So it's by default, any Kubernetes clusters allows enough interfaces using which the next set of new or custom feature can be added to the existing cluster. Okay. Next talks about self-healing feature of Kubernetes. This is very important, right? So let's say that you have built one cluster, it is running, it is managing your hundreds of thousands of containers, okay? And you as a user have defined what is the steady state of the system, which may mean that at a given point of time, for a container A, minimum 3 instances of it must be running. Max it can go up to 6, okay? And the container should be running in a good way with the container health remains good. Right? Let's say that's the minimum set of guidance that you have rolled out. Now, Kubernetes will monitor the cluster health, the container health for you. It will also monitor the number of instances of this particular container is running. Okay, it will check if it is less than the minimum or it is more than the maximum, right? And depending on that, it can take certain decision, okay, to spawn more number of containers, to spawn less number of containers, to kill a particular running container if it is more than the max number of containers, okay, for that particular service. It can also check, okay, let's say we deployed one particular update. After the update is deployed, container's health became bad, then the Kubernetes can take decision to roll back that particular update so that the container can go back to the healthy state again. All of this is automated. Okay. Then we come to service discovery and load balancing. So container receives IP addresses from Kubernetes while it assigns single domain and system name to a set of container to add in load balancing request across the container of the host. Okay. Again, what exactly it means? So you are running, let's say, 10 containers of the same, or let's say 10 container instances of the same microservice. Okay. Now, even though we are running 10 instances of the microservice, we do not want to expose 10 different DNS name or IP addresses to the service or the user who is going to use this microservice, right? So what Kubernetes allows, it allows us that the face or the interface of all of these different 10 containers remains one single IP address, one single DNS name. Okay, and with that, not only it can expose to the end user, to the to the service which is going to use this particular microservice or container, a single name, single IP address. Also, this interface allows for the load balancing. Okay, for example, let's say 100 requests are coming for getting this service, for which we have 10 different instances running. The face of these services, which makes sure this 10, 100 requests which are coming in get equally distributed across all of these 10 microservices. Okay, so it becomes easier for the end user, for the end service to talk to different services inside the cluster, okay, and easily discover the nodes or the endpoint it want to talk to. Okay, so we briefly touch base upon automated rollbacks and rollouts, which simply means if you want to upgrade your applications or upgrade your containers to a newer version of the software, all you have to do, you have to go and update the config files of that particular container, and that Kubernetes system will take care that all the running instances of that container on this cluster get upgraded automatically. Similarly, if you don't get a particular version in the config file, you have to do it once, and that's all. I mean, Kubernetes will take care of the rest. We also talked about the self-healing feature, which is automatic rollback feature, basically, because the things are not in good state. Then we talk about secret and configuration management. This is the place where, let's say, for a different container or for some container, you have some sort of secret parameter to pass to. It may be username, it may be passwords, okay, which you don't want to expose in the human readable config files. Okay, so this is also one thing which Kubernetes provides a very good facility where you can keep your secrets in a database in encrypted format so that end user or the unwanted user never gets to know what exactly the secret keys are. Okay. With that, let's talk about the batch execution. Batch execution is the thing where Kubernetes allows you to schedule some sort of job to execute in batch in the background. So we have discussed that there can be different microservices which may be running, which you can schedule. But other than this microservices, there could be this maintenance jobs which you want to schedule on your cluster so that they can do some sort of bookkeeping on your system, or some cleanup services on your system, or some backup services on your system. All of that can be scheduled in batches. The Kubernetes provides that facility. And then by default, Kubernetes allows you to have IPv4 and IPv6 dual stack services. So all of your containers, microservices, um, by default can have access to IPv4 and IPv6 stacks. Okay. So now let's talk about the Kubernetes architecture in detail. So this picture at the high level talks about what Kubernetes architecture look like. And if you really see, there are basically a number of nodes. And then we can see there is a one control plane node. And then we have certain components lined up in the right of the slides. We will discuss them in detail. But in general, the idea is one Kubernetes system would have multiple nodes. This node can be categorized into two categories. We can call them control plane nodes or the worker nodes. Okay. Now, in a typical system, you will have more than one control plane node. Minimum one control plane is must. And then the worker nodes are going to be more than one, and worker node scale as per demand. So if worker node basically decides the size of your cluster. This is where your actual microservices would be hosted, which is your business specific microservices. Okay. So the control plane nodes provides a running environment for the control plane agents. Okay. And these control plane agents or the control plane services are responsible for managing the state of a Kubernetes cluster. Okay. The control plane services can be termed as the brain behind all operations inside the cluster. Okay. And each of the microservices which run on the control plane, they have distinct responsibilities. Okay. And combined together, they ensure the state of the Kubernetes cluster remains as we expect it to be. Okay. And also, this control plane services provides endpoint to the end user using which the end user or the user outside of this cluster can talk to this Kubernetes cluster using some sort of API interface. Okay, so we will go into detail. So this slide gives a little bit more easier understanding how the things are. So here you can see you have one control plane node. Don't mistake it. You can have more than one control plane nodes in the system. But in this picture shows only one. Worker node, most likely you will have, in a reasonable cluster, you will have hundreds or tens of these worker nodes, and these will host user containers basically. Okay? And then you can see some of the processes which are running on control plane nodes, also on the user plane nodes or worker nodes are kube proxy and kubelet, and we will discuss about them in detail in the next few slides. Okay, so this is the basic architecture of Kubernetes, and one of the things which makes Kubernetes what it is something called etcd. It is shown in the slide here. etcd is the key value store. It is a very fast, persistent, and consistent storage which allows to store unique state of the system, and with that, system or Kubernetes processes can explore the correct state of the system whenever they want to. So etcd you can think of as a backbone of this entire system. Okay, so here let's talk about the main processes of the control plane side. So we have API server. What API server is, as the name suggests, right? It hosts the APIs. What are these APIs? APIs are the interfaces through which a user application or a user can talk to Kubernetes cluster. So this is the only endpoint user is exposed to in terms of managing Kubernetes. So API server will host these APIs, and it will validate them, it will authenticate them, and it will call other services in the Kubernetes cluster on the control plane side to take certain actions based on the user request and provide response to the user. Okay. The scheduler, as the name suggests, its main job is, as per user request, as per user configuration, it deploys different containers into different nodes based on their resource requirement, based on the load requirements, etc. Okay. Then we have the controller manager. The main job of the controller manager is to keep, so it keeps on monitoring the state of the system. What I mean by state of the system is that it keeps on monitoring the defined state of the system which user is expecting. It matches that with the current state of the system, the way it is currently. And based on that, if the current state of the system does not match with the expected state of the system as defined by the user, it can take certain actions so that at any given point of time, the desired state of the system matches with the current state of the system. Okay. We briefly talked about key value data store. This is etcd in Kubernetes makes mostly. So this is where all of these key and their values are stored. Okay. This allows for Kubernetes to work as it is expected to work. So the current state of the system, the desired state of the system, user-defined state of the system, all the spot properties, all the job properties, the different configuration of the node, the different configuration of the various services, the control plane services, the worker node services, all of that is stored in the form of key value in etcd database. Okay, so etcd is an open source project under the Cloud Native Computing Foundation. And etcd is a strongly consistent distributed key value data store used to persist a Kubernetes cluster state. One of the thing about etcd is that whenever you write a new data to etcd cluster or etcd data store, it does not remove or erase the old data, but it appends the new data to the old data. And then there are services which runs periodically to compact this overall data. What this allows that from any point of time, you can go back to the past and restore the system state to some values in the past, because system never forgets the state of the system in the past, because it is never releasing or it is never deleting the data in the key value data store. On top of that, there are other components such as container runtime, node agents. Node agents are basically kubelet and proxy. And then we have some other add-ons like DNS server. We have dashboard for Kubernetes. So all of these things are there on top of the basic components. Okay, so let's go to the next one. So we have worker node components. So what are the main worker node component we have? So we have container runtime. Kubernetes by default does not provide container runtime. If you remember, container runtime is the facility by which container can run on the host operating system. Kubernetes does not have inbuilt container runtime, but it allows for the interfaces through which different container runtime can interact with the Kubernetes system. Okay. Then we have a node agent called kubelet. Kubelet is the agent which is running over each of the nodes of the systems, and this kubelet agent talks to the container runtime to manage the containers, basically. So at one end of the kubelet, it would be talking to the API server, most likely, and or the scheduler. On the other end of the kubelet, it would be talking to the container runtime to manage the different containers. The kubelet is the service or the agent running on each of the nodes to manage the different containers based on either API server's request or scheduler. Then we have kubeproxy. Kubeproxy is nothing but kubeproxy is the main how to say networking service running on each of the node, and kubeproxy creates this complicated networking rules routing tables so that your single DNS name can be represented or hosted by multiple pods or containers underneath them. All of this scheduled on a single node or a multiple worker nodes. But with the help of kubeproxy, it is ensured that you can assign one single DNS name to your service That name can be exposed to your end user, and when the requests are hitting this DNS name, this kube proxy ensures that underneath this request hits one of those ports deployed under this DNS name. It's a little bit complicated. We will discuss this in detail in the next few slides. And then we have the add-ons like the user interface, dashboard, and monitoring and logging services. Okay. So one of the things that you have to understand in Kubernetes, and all the time people will talk about something called pods instead of containers. So we need to discuss, we need to understand what is the difference between a container and a pod. Because when people talk about Kubernetes, they will be talking in terms of pods. Okay. So this is a high level, again, architecture of a worker node. In a worker node, you will have one or more pods. Okay. And this pod, inside this pod, you might have one or more containers. Okay. Now the question would come, hey, why we need pods? Why can't we simply have containers? The reason is Kubernetes, for the sake of simplicity of the architecture, treats each of these pods at a high level as a VM. Okay. So these are not VMs, but this appears as a VM like virtual machines like hosting environment for this container. So all of these containers which are running inside one pod, they would share the resources of the pod, including the networking space of the pod. The memory of the pod, they share the same memory, so memory can be shared across different containers within the same pod. Okay. So at the high level, a worker node provides a running environment for client application. These applications, which we can also call microservices, they run in a container, and then we run this container in something called pod. And when Kubernetes schedules these containers, they do not generally schedule a container itself. They schedule a pod which is hosting a container. So you can say that pod becomes the smallest scheduling unit inside a Kubernetes world. In this picture, you can see in the top level picture, you have only one container, and that pod has one IP. So that container called app1 gets this IP pod IP. In the below picture, we have two containers, and again, this pod gets a single IP. Both of these containers, which are running in side pod 2, are going to share this IP. And of course, the way it works on a host system, it has to be ensured by the networking system of the Kubernetes, for this example, kube proxy and all, that these different containers use different port numbers so that the right request can be routed to them. Now, one thing we need to understand, pods are ephemeral units inside Kubernetes. What this means is pod can be easily deleted, or they can be easily deleted or destroyed. When they come back again, so when you, let's say you delete one pod, with that, all the container inside that pod will be deleted. If that pod itself is not using any persistent storage, then all the data which this pod or container had will be lost, along with this IP address which this pod was assigned. So when you start a new pod, it will start fresh, and it might get a fresh IP as well. So in a Kubernetes world where we are creating and destroying pods all the time, how do we ensure that end user can talk to a application reliably, right? How do we ensure that? So for that, there is a concept of service. The service runs on top of pods. So general architecture would be that there would be a pod would expose certain endpoints which service would point to, and then service would be exposed to end user. Now, as long as this endpoint which pod is exposing towards service remains unchanged, which means as long as nobody messes up with the configuration of the pod itself, we can create and destroy pods as many times as we want, but end user can still talk to the application using the service endpoint. Because service will not be destroyed along with the pod, service will still be available, and service will make sure that it can attach to the new pods as and when they come up. So for the end user, application is always available. And this is one of the way Kubernetes ensures high availability, because underneath it can have hundreds of containers. Some of them will go down, but this service running on top of it ensures that it can route the request to one of these containers which are available. And then there are two categories of service. One is called ingress service, one is a normal service. Normal service are used to talk to the containers or the pods within each other. And then generally egress service is the one which acts as the load balancer and which is exposed to the outer world. Okay. So let's go a little bit deep in the Kubernetes runtime. So we have certain flavors of the Kubernetes runtime. One is called CRIO. Okay, a lightweight container runtime for Kubernetes. Okay, then we have containerd. This becomes the default, and this was a portable container runtime now comes as a default with the most Kubernetes deployment. In the early days, we had the Docker engine, which is used for the most popular version for the container runtime or the container families, which is Docker. And then we have the Mirantis container runtime. Okay. So these are the most common choices that one can have when integrating their container runtimes or their container system with Kubernetes. The way these different flavors of the Kubernetes runtimes, oh, sorry, not Kubernetes runtime, container runtimes, pardon me, can be integrated with Kubernetes is something like this. So we will have a Kubernetes utility, Kubernetes agent called kubelet, which would be running on each of the node. This kubelet using gRPC client can be connected to something called gRPC server. This gRPC server will be hosted by the CRI shim, which is nothing but container runtime interface shim, and which will be container connected to container runtime. So this kubelet service knows how to talk to the CRI shim, okay, which provides standard interface towards kubelet service. All one have to do to integrate a container runtime with kubelet, they will have to implement if this CRI shim, if it is not already available. And this CRI shim is responsible for managing, let's say, requests from kubelet and converting them in the form of API, which container runtime understands, and then maintains or executes the request for the kubelet using container runtime. Okay. So in this way, if you really see, container runtime does not have to change. It is exactly same as it was for any standard deployment, whether it is Kubernetes or not. Same way, kubelet is not writing new code to talk to different container runtime. It is making standard calls only. Only thing which is new here, which is used to integrate these different container runtimes with kubelet is this CRI sim. This has to be written for any new container runtime which is not already integrated with the kubelets or Kubernetes. Okay, so in a way, kubesim is nothing but an abstraction layer between container runtime and kubelet. Okay, so a little bit more detail about this. This says originally Kubernetes was tied to Docker, then Kubernetes being Kubernetes. They do not want to give reference to any specific version of the container runtime. So they moved away with that, and now there's no specific preference for this. Right now, most default item is CRI Docker container D or Docker D are the daemons or the standard interface, which becoming more of a default with the Kubernetes community. Okay. So CRI doc container D allows container to be directly created and managed with container D at kubelets request. Then we have CRI-O, which enables the use of any open container initiative compatible runtime with Kubernetes, such as runc. So all of this, CRI container D, CRI-O, and then we have Docker shim or CRI Docker D. All of these are the shims or the container runtime written for managing container runtime or for managing the lifetime cycles of the containers. Okay? And Kubernetes has generally Kubernetes being a popular platform now, somebody has written this shims or this abstraction layer so that all of these open initiatives of the container runtime can work seamlessly with the Kubernetes engine. Okay, with that. So kubeproxy we briefly talked about. We are just repeating what we said that in a way, not in a way, the kubeproxy is basically responsible for dynamic updates and maintenance of all networking rules on the node. It ensures different nodes we can talk to each other, different containers can talk to each other, different containers on different ports can talk to each other, different pods on different nodes can talk to each other, or different pods on different clusters can talk to each other, as long as they're on the same Kubernetes system. And then they have certain add-ons. DNS provides a unique name to the services so that you can have multiple pods. They may come and go, but user can access those services reliably. Kubernetes has a basic dashboard in the form of add-on, and though it is not as powerful as some of the command line utilities like kubectls and all, but still you can play around with this dashboard and see a lot of things. And then there are add-ons for monitoring and logging. Okay, so with that, we move to one of the complicated topic of Kubernetes, which is Kubernetes networking. Okay, and there are multiple ways. If you think about the pods can communicate with each other or container can communicate to each other. So as we said in the beginning, right, within the same pod, you can have two containers or more than one container. So there are those computer containers are talking with each other. Okay, and then we can have pod-to-pod communication where there are two pods, they're talking to each other, or the container inside two different pods are talking to each other. Okay. Then we have service to pod communication where there is a pod, there is a service on top of it, and then these pods or these services are talking to the pods or all the pods which this service is responsible for. And finally, we have external to service communication where there is an external service which is talking to what outside of Kubernetes cluster. Okay. So decoupled microservices-based applications rely heavily on networking in order to mimic the tight coupled ones available in monolithic area, right? So if these applications were a monolithic application, a user could have just talked to them very easily with using a unique IP address or DNS name. User experience should not change too much, right? Just because you have moved from monolithic application to cloud native application. So this networking facility or rules which Kubernetes provides, it ensures that the user experience does not change too much. Okay, how it works. Technically speaking, this entire system works on two things. One is the networking namespace feature of the Linux operating system, which allows that different pods can have different namespaces. Okay, so every time we spawn a new container, underneath container runtime would create something called a pause container, which would have a dedicated namespace for it, networking namespace, file namespace, etc., using which it is ensured that this particular pod will have a unique namespace for networking. But this means that all the IP addresses which are assigned inside this pod, they remain unique to this pod only. There is no conflict outside this pod. Okay, and then we have this networking rules, routing rules, etc., which kubeproxy maintains, so that the communication which is supposed to go outside of pod, that goes outside of pod. Okay, all of this routing is created properly so that it knows the service discovery can happen, so that it knows like which IP address is sitting on which MAC address, where to go, where how to route across it. Okay, so let's discuss a little bit in more detail about each of these cases. First one is intra-pod communication. Okay, so how it works at the high level, container runtime would create something called a pause container so that for each of the new containers, so each of the new container gets created. Along with that, container creates a pause container that would allow a dedicated namespace only for this particular container that we are creating, this particular pod that we are creating. And now all the container inside this pod will share the namespace of the pod and they can talk to each other. As if the different processes running inside the same operating system. Okay. Then we have interpod communication, and as we discussed, interpod communication is mostly managed by kubeproxy, and the way kubeproxy can manage them is can be with the help of this CNI. CNI is nothing but container network interfaces. This the way it works that depending on the platform, user can decide, or the operator or the vendor can decide, or the administrator can decide, okay, these are the networking model that I would like to use, using which my different pods can connect with each other. So what they have to do, so Kubernetes provide these CNI interfaces, container runtime interfaces. People can implement their plugin following these interfaces, and they can implement the plugin to work with whatever networking facility they have underneath. So for example, we can have this Mac VLAN interfaces, we can have the Linux bridge, we can have third-party plugins for the networking, whatever it is, maybe TPDK or something. All of this works. All of this works with the same Kubernetes architecture without touching any of the core Kubernetes code, because Kubernetes exposes this networking facility in the form of CNI interfaces. All people will have to do, whoever want to extend the Kubernetes container to their own environment, to search for if there is already existing CNI plugin for that. If there is no such plugin exist, they can implement this plugin for their own network um, infrastructure. But most likely, Kubernetes being so popular nowadays that most likely any platform that a user might have, there would be a CNI plugin for that. And all one have to do is add that. as an add-on to your cluster. If it is not already there, by the way. Most likely it is already available as an add-on when you create the cluster. Okay. And then external communication to pod. External communication happens through services, especially egress services, and this network routing rules, which is required for the external communication, is managed by the ITP tables, and all of those rules are created and managed by the kubeproxy agent, which is running on each and every node. Okay, so with this, we will stop this video over here. In the next video, we will discuss the various deployment options that we have in Kubernetes, and we will talk about Minikube, one of the simplified, most simple way of deploying Kubernetes cluster to play around and to learn about it. And then we will have a demo just to have the different flavors of Minikubes, deployment options, and how can we have our own first cluster up and running. So till then, bye-bye.